to inject quantum mechanics into our understanding of things like black holes, and that's where Hawking proved that black holes are not completely black. Astrophysics, the branch of science that seeks to understand the universe and the way it works, has long been interested in the mysterious concept of black holes. Black holes are regions in space with such immense gravitational pull that nothing, not even light, can escape from them. Their existence was first theorized through Einstein's theory of general relativity in the early 20th century. Over the years, extensive research and observations have reinforced their significance in our understanding of the cosmos. One of the tools researchers use to figure out the realities of space is the James Webb Space Telescope. While it wasn't meant to study black holes since the focus is on the entirety of observable space, it's bound to pick up information about black holes too. However, the problem is that the information it's picked up is the exact opposite of what we were expecting. Greene has just confirmed the recent findings, and it turns out, according to the James Webb Space Telescope, black holes aren't real. Join us as we bring you all the details. Telescopic imagery from the Event Horizon Telescope of the black hole in M87 that ripped on the fabric of space was the most direct evidence about this shocking discovery and how it's turned the world of science upside down. Black holes are cosmic entities predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects deform the entire fabric of spacetime, creating what we perceive as gravity. When a star runs out of its nuclear fuel and undergoes a supernova explosion, its core collapses under the sheer force of gravity. If the remaining mass exceeds a critical limit known as the Chandrasekhar limit, the gravitational collapse becomes irreversible, leading to the formation of a black hole. Even with that, black holes have always been theorized about since their initial discovery. While black holes themselves can't be directly observed because of the way they're created, scientists have identified several key characteristics and properties through indirect observations. As light from background stars or galaxies passes near a black hole, its path is bent by immense gravity, creating a gravitational lensing effect. While it sounds absolutely trippy, it's the only thing that allows astronomers to detect and study black holes indirectly by actually studying their gravitational influence on surrounding objects. So, what's around the black hole is very important here. When matter from nearby stars or gas clouds falls toward a black hole, it forms an accretion disk around the black hole. These vibrations created by the black hole rippling through the gas cloud are then picked up on the planet Earth, massaged by a computer, and amplified by 57 octaves. The material in the disk becomes superheated and emits X-rays, providing another observable signature of black holes. The vision or interaction of black holes with other massive objects can produce gravitational waves, ripples in spacetime, which were directly detected for the first time in 2015. There are both very old and new observations that have been made over time. Over the decades, extensive astronomical observations and advances in technology have provided quite compelling evidence supporting the existence of black holes. Gravitational lensing has offered a look into the distorted light from background objects, indicating the presence of massive objects with intense gravitational fields. Plus, X-ray emissions from accretion disks around invisible objects have matched theoretical predictions for black holes. Not only that, but the detection of gravitational waves specifically from the merger of black holes has provided direct confirmation of these powerful entities. The James Webb Space Telescope is a technological marvel that was created to revolutionize astrophysics, and it has not disappointed in its mission to uncover the secrets of the cosmos. As researchers eagerly wait for its data, they were not prepared for the astounding revelations it would bring. Armed with this state-of-the-art observatory, scientists went on a journey that led them to make extraordinary claims that challenged the very existence of black holes. Yes, researchers utilizing just 2 sets of data have reported intriguing phenomena that appear inconsistent with our traditional understanding of black holes. Some of these findings have pointed to the possibility of alternative explanations for the things we always thought were proof of black holes. And, well, let's just say that the world of space exploration has done a complete 180. One of the problems has to do with gravitational lensing. With the JWST's advanced observational capabilities, researchers are expected to witness familiar gravitational lensing patterns that align with our understanding of black holes. The light should bend, there should be that big black hole of nothingness that's causing light to distort. However, some of the observed gravitational lensing events presented strange results. You know, when matter falls toward a black hole and forms an accretion disk around it, the superheated material emits X-rays which are detectable by telescopes. These X-ray emissions are among the key observable signatures used to identify black holes and study their properties. If the black hole's mass goes up by the amount of mass that falls in, but even that concept is being turned around on its head. With the JWST, scientists have scrutinized regions suspected to contain black holes, observing their X-ray emissions in greater detail. Unexpectedly, certain black hole candidates have shown peculiar patterns in their X-ray emissions that challenge the conventional understanding of these cosmic entities. The expected variations in X-ray brightness, spectral characteristics, or timing properties have left researchers wondering if traditional black hole models adequately account for these emissions. This uncertainty has given rise to alternative explanations that explore the possibility of other exotic compact objects or modified gravity theories. One of these has to do with gravastars. These hypothetical objects have captured the imagination of astrophysicists as they present a unique twist on the classic black hole theory. In the gravastar model, the exterior still appears similar to a black hole, following the well-known metric that describes gravity's behavior around such massive objects. However, a fascinating twist lies within its core. Instead of a singularity like the one postulated in traditional black holes, gravastars have more of a distinct metric inside. What takes things even further is its event horizon, which hosts a thin shell of matter. This peculiar configuration sets gravastars apart from conventional black holes and prompts scientists to consider intriguing possibilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, has also played a pivotal role in our overall journey to explore the cosmos. Detecting gravitational waves from distant cosmic collisions has allowed LIGO to provide valuable insights into the nature of compact objects. Plus, in some instances, the gravitational waves detected by LIGO have also exhibited characteristics that are completely indistinguishable from those of ordinary black holes. So, something is going on here. In the realm of astrophysics and general relativity, the no-hair theorem has long stood as a prominent principle shaping our understanding of black holes. According to this theorem, all stationary black hole solutions to the Einstein-Maxwell equations, which describe the gravitational and electromagnetic forces, possess a unique set of characteristics. These specific attributes are the black hole's mass, angular momentum or spin, and electric charge, collectively referred to as the black hole's hair. The no-hair theorem suggests that any other distinguishing features of a black hole beyond its mass, spin, and charge are considered hair and are believed to be lost beyond the event horizon. This event horizon acts as an impenetrable boundary beyond which information is seemingly irretrievable from an external observer's perspective. To put it in one sentence, conventional black holes have been thought of as relatively simple and devoid of any further distinguishing properties. However, in a remarkable study, Sasha Hacko, Stephen Hawking, Malcolm Perry, and Andrew Strominger challenged this traditional view of black holes. Their groundbreaking research presents the existence of what they call soft hair in black holes, suggesting a more complex structure than anyone previously thought about. Soft hair refers to a collection of quantum properties that are thought to reside on the black hole's event horizon. Unlike conventional hair, soft hair is not associated with the black hole's mass, spin, or electric charge. Instead, it is believed to have subtle quantum properties that encode information about the black hole's interactions with its surrounding environment. The existence of soft hair would have profound implications for our understanding of black holes and the nature of information in the universe. It could potentially resolve long-standing questions related to the information paradox concerning what happens to the information of matter that falls into a black hole. The idea of soft hair hints at the possibility that black holes may retain subtle quantum fingerprints of their past interactions, raising the exciting prospect of retrieving information that was once thought lost beyond the event horizon. And if that's true, then what the James Webb Space Telescope found would be true too. But if you reel things back in time a little bit, this concept has actually been there for a really long time. Back in 1974, Stephen Hawking proposed a groundbreaking idea called Hawking radiation. According to this, black holes emit radiation over time, which causes them to lose mass and eventually disappear. At the time, though, this radiation seemed to be random and didn't carry any information about what fell into the black hole, which clashed with the principle of information preservation in quantum theory. Scientists did try to combine quantum theory with gravity to solve this paradox,
but they ran into mathematical problems and couldn't make sense of it. The situation seemed quite confusing, and this is probably why the theory didn't actually pick up and somewhat disappeared as the world of science went on. However, a recent study led by Netta Engelhardt and her team made exciting progress. They re-examined Hawking's formula and found a new calculation suggesting that information does escape black holes through their radiation after all. The revised formula proposes that the radiation carries subtle traces of the lost information inside the black holes. As the black holes evaporate, they emit this radiation, revealing some details about the matter that had fallen into them. This discovery is a significant step forward in understanding the information loss paradox and bridging the gap between quantum theory and gravity, and at the same time, it flips the traditional theories of black holes completely. Both dark matter and dark energy are two mysterious components that make up a significant portion of the universe, yet their nature remains elusive. While black holes have long been considered the primary explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy might play a role in these cosmic phenomena. Dark matter is an invisible, non-interacting substance that exerts a gravitational pull, affecting the motion of galaxies and galaxy clusters. It is thought to be responsible for the observed gravitational effects that have traditionally been attributed to black holes. Some scientists propose that the dense concentrations of dark matter could create regions of immense gravitational influence, mimicking the gravitational pull typically associated with black holes when in fact, it's just dark matter. Dark energy, which is believed to be responsible for the accelerated expansion of the universe, could also impact the gravitational behavior of cosmic structures. Although dark energy's effects are usually associated with large-scale phenomena, it won't be too much of a stretch to think that its influence on local gravitational interactions might also yield results similar to those traditionally linked to black holes. Exploring the roles of dark matter and dark energy in the formation and behavior of cosmic objects such as galactic centers might shed new light on our understanding of black hole phenomena. By investigating these alternative explanations, scientists aim to uncover more about the intricate interplay between gravity and the mysterious constituents of the cosmos. Another intriguing avenue of research involves alternative theories of gravity that challenge the traditional concept of black holes. In the realm of modified gravity theories, scientists propose adjustments to Einstein's theory of general relativity to explain gravitational phenomena without invoking the formation of black holes. These alternative theories posit that gravity may behave differently on cosmic scales, especially under extreme conditions. Rather than a complete gravitational collapse leading to a black hole singularity, modified gravity theories suggest that other outcomes are possible, such as a gravitational collapse stopping at a certain point. One prominent example of a modified gravity theory is modified Newtonian dynamics, MOND, which aims to account for observed galaxy rotation curves without the need for dark matter. It was brought forward by physicist Mordechai Milgrom, who was also looking for ideas to explain what happened in space in the early 1980s. The rotation curves of spiral galaxies are quite strange. According to Newtonian gravity, the gravitational force experienced by objects within a galaxy decreases with distance from the center, so stars and other visible matter in galaxies should follow a specific pattern of orbital velocities as they move farther from the galactic center. However, observations reveal a different story. Instead of following the predicted pattern, the rotation curves of spiral galaxies indicate that the orbital velocities of stars remain roughly constant or even increase as one moves away from the galactic center. This unexpected behavior has led to the hypothesis that galaxies contain a significant amount of unseen or dark matter that exerts an additional gravitational pull, explaining the strange rotation curves. Instead, it arises as an emergent phenomenon from the collective behavior of underlying microscopic building blocks. In the framework of emergent gravity, Eric Verlin suggests that gravity is not an independent force like electromagnetism or strong and weak nuclear forces. Instead, it emerges from the interactions of numerous elementary constituents that form the fabric of spacetime itself. Verlin's idea builds upon the concept of holography, a fundamental principle in theoretical physics. Holography posits that the information describing a three-dimensional space can be encoded on its two-dimensional boundary. What Verlin proposes is that gravity, traditionally thought to be a fundamental force that permeates the fabric of spacetime, emerges as a result of information processing on a holographic boundary. The concept of holography, a fundamental principle in theoretical physics, serves as the basis for Verlin's proposal. Holography asserts that the information describing a three-dimensional space can be encoded on its two-dimensional boundary. According to this perspective, the interactions and dynamics of the elementary building blocks of the universe at the holographic boundary give rise to the perception of gravity. As these microscopic constituents collectively interact and exchange information, a gravitational-like force emerges on a larger scale, similar to the way gravity manifests itself around massive objects. In Verland's theory of emergent gravity, the concept of entropy plays a central role. Entropy is a fundamental concept in thermodynamics and is often described as a measure of disorder or randomness in a physical system. It is also closely related to the amount of information contained in the system. Verland draws a profound connection between entropy and the perceived force of gravity. According to his proposal, when there is a redistribution of information within a system, there is a corresponding increase in entropy. This increase in entropy leads to the emergence of an apparent gravitational force, much like how gravity arises in the presence of mass in traditional physics. The force of gravity is associated with the presence of mass, where massive objects curve the fabric of spacetime, causing other objects to move in their gravitational field. In Verland's emergent gravity, the force of gravity is connected to the redistribution of information, which is quantified by the change in entropy. As the microscopic constituents of the universe interact and exchange information on the holographic boundary, the information within the system changes, leading to changes in entropy. This change, in turn, gives rise to an apparent gravitational force on a larger scale, creating the perception of gravity that we experience in our everyday lives. The connection between entropy and gravity in Verland's theory is a fascinating departure from conventional notions of gravity as a fundamental force tied to mass. The problem opens up a new way of understanding how gravity may be intricately linked to the informational aspects of the universe. And if gravity isn't quite the same as we'd always thought it was, then the entire basis of what makes a black hole what it is challenged too. But the problem here is that how could something so powerful be totally false? Is that even possible? Well, yes. Observing and studying black holes pose significant challenges due to their nature and the vast distances involved. Observational limitations have played a crucial role in shaping our understanding of black hole signatures, and at times, they may have led to misinterpretations. As we've discussed earlier in the video, accretion disks are essential for understanding the behavior and properties of black holes, but in the past, telescopes faced significant challenges when attempting to study these accretion disks in detail. Their limitations in resolution and sensitivity hindered a direct view of the accretion process near black holes. The accretion disks around black holes are typically relatively small and distant, making them difficult to observe with the precision required to grasp their intricate features. To overcome these limitations, scientists resorted to indirect measurements and studied the X-ray emissions from the accretion disks. Since X-rays are highly energetic and able to penetrate obscuring dust and gas, they provide valuable information about the presence and characteristics of the accretion process. But the thing is, relying solely on X-ray observations had its drawbacks. The lack of direct observations meant that some aspects of the accretion process and the black hole's properties remained unclear. For example, the exact structure and dynamics of the accretion disks, as well as the distribution of matter within them, were not fully recognizable from indirect measurements. As a result, misconceptions or incomplete understandings about the nature of the accretion process and the black hole's behavior may have emerged. But that's not the only place an issue could have come from. While gravitational lensing offers exciting insights into the properties of black holes, interpreting these observations accurately could be challenging, especially when multiple lensing effects overlap. In some cases, a single black hole can produce multiple lensing events, leading to complex and intricate distortions in the observed light. One of the difficulties lies in extracting the various lensing effects and attributing them to specific black holes or gravitational objects. Previous telescopes had limitations in their capabilities, such as resolution and sensitivity, which made it challenging to resolve and differentiate overlapping lensing phenomena. These limitations could have introduced errors in deducing the characteristics of black holes and the matter surrounding them. For instance, when studying the lensing of a distant quasar or galaxy, scientists may observe multiple images of the same background object due to gravitational lensing by intervening black holes or galaxy clusters.
The positions, shapes, and brightness of these multiple images can provide valuable information about the lensing mass and the geometry of the gravitational field. But the thing is, disentangling the lensing contributions from various intervening objects demands precise and high-resolution observations. Another thing here is the fact that black holes are frequently found in bustling cosmic neighborhoods, such as dense stellar clusters or at the centers of galaxies. These regions are bustling with various celestial objects, including stars, gas clouds, and other massive bodies. But their crowded nature poses significant challenges for telescopes attempting to study black holes and precisely locate them. In the past, telescopes had to deal with a bunch of limitations in their ability to resolve individual sources within these densely populated regions. The resolution of a telescope determines its capacity to differentiate closely spaced objects and discern fine details in their structures. In the context of crowded areas with numerous celestial bodies, telescopes might struggle to achieve the necessary resolution to clearly distinguish each individual source. This ambiguity in identification could lead to uncertainty about the exact location of the black hole within the cluster or the galaxy's central region. On top of that, without clear resolution, telescopes may not be able to discern the unique characteristics of a black hole, such as its gravitational influence on nearby objects or the specific emission signatures from its accretion disk or surrounding gas. This limitation ends up being a problem for a comprehensive understanding of the black hole's properties and behavior. Analyzing the spectra of black hole candidates is crucial for gaining insights into their properties and understanding their behavior. The spectral data obtained from black holes contain valuable information about the composition, temperature, velocity, and other essential characteristics of the surrounding matter and the black hole itself. However, obtaining high-quality spectral data from black holes can be challenging, and there are a few key reasons for it. Black holes often emit faint radiation, especially in certain wavelength ranges, making it difficult to detect and measure their spectra accurately. The faint emission can be overwhelmed by the brightness of nearby stars or other celestial objects, leading to challenges in isolating and analyzing the black hole spectral signature. Because of the faint nature of black hole emission, telescopes often need to collect data over extended periods to accumulate enough photons for a meaningful spectrum. Longer exposure times may be necessary to improve the signal-to-noise ratio and obtain reliable spectral information. But this requirement for lengthy observations can pose practical challenges, particularly in cases where multiple observations are needed. Spectral features such as absorption and emission lines provide crucial information about the properties of the material surrounding the black hole. But the thing is, identifying and interpreting these lines accurately can be complex, especially when they overlap or when multiple components contribute to the observed spectrum. Insufficient spectral data may lead to an incomplete understanding or misinterpretation of these lines. Black hole systems can also exhibit spectral variability over time, with emission features changing due to variations in accretion rates or other factors. Capturing these spectral changes requires multiple observations at different time points, and insufficient data might result in an incomplete picture of the black hole system's dynamic behavior. All of these things combined make it obvious that we can't rely on information from the past, at least not entirely. There's a massive need for something to gather concrete information in as much detail as possible, and that's where the James Webb Space Telescope comes in. The James Webb Space Telescope is one of the best instruments for studying black holes due to its unique and advanced capabilities. As a space-based observatory, the JWST offers several advantages that make it particularly well-suited for probing the mysteries of black holes. For starters, the telescope is designed to operate primarily in the infrared wavelength range, which is crucial for studying black holes. Infrared light can penetrate dust and gas, providing clearer views of regions obscured in visible light. This sensitivity enables the JWST to study the emission from black holes' accretion disks and their surroundings, even in heavily obscured environments. It also boasts superior spatial resolution compared to previous infrared telescopes, meaning it can resolve finer details and distinguish closely spaced objects, allowing scientists to pinpoint the exact locations of black holes within crowded regions, such as dense stellar clusters or the centers of galaxies. The spectrographs that the James Webb Space Telescope brings in can disentangle complex spectral features, including absorption and emission lines. This capability is essential for analyzing the composition, temperature, and velocity of the material surrounding black holes, shedding light on the nature of accretion and other physical processes, which for the most part have just been theorized about this whole time. Although the JWST operates outside Earth's atmosphere, it is equipped with adaptive optics that correct for residual distortions. This technology further enhances the telescope's spatial resolution, enabling clearer and sharper images of black hole systems. But even if you take all of that out, there's one thing that puts it above everything else, literally. The JWST's position in space allows for extended and uninterrupted observations, overcoming the challenge of long exposure times needed to study faint black hole emissions. Longer observation times enhance the signal-to-noise ratio, resulting in higher quality spectral data and more robust scientific findings. Because of that, it can observe black holes at various infrared wavelengths, providing a comprehensive view of their properties. Multi-wavelength observations enable researchers to study different aspects of black hole systems and gain a more complete understanding of their behavior, or lack thereof. Plus, there's also the fact that the JWST is an international collaboration between NASA, ESA, and CSA, bringing together the expertise of scientists from around the world. This collaboration is great because there's an exchange of ideas and pooling of resources, maximizing the telescope's potential for groundbreaking discoveries in black hole research. So even if one department has a bias or is confused about a certain discovery, they have more than enough people at their disposal to make sure that all of the data that makes it to the public is proven and reliable. With all of that, there's nothing better than the JWST to bring in information about black holes or to prove that they never actually existed in the first place. But which side of this argument do you land on? Let us know in the comments below. If you liked this video, please give it a thumbs up, and like always, we'll see you in the next one.